Okay. So this is what we were talking about last lecture about irreversibility theorems. We were studying the Markov property, that is the case where you have saturation of a strong subadditivity, you have three Hilbert spaces, 1, 2, and 3, and you have this relation for the entropies. And yesterday, some of you asked me if there was a simple interpretation of the result that somehow the state in 1, 2, and 3, the correlations between 1 and 3 were intermediated by the region 2. And one simple way to say that is, suppose you have a correlation here, or some part of 1 and some part of 2, and some other part of 2 is correlated to 3. Then you can write this this relation in terms of the mutual information, and it's just tell you that mutual information saturates. The mutual information between 1 and 2 is equal to the mutual information between 1 and 2, 3. And this means that adding the region 3 to the region 2 does not increase the correlations between with the region 1. And somehow is what happened here. It doesn't matter that there are correlations between 2 and 3 because they will not affect the correlations with the region 1. We were studying this for because we thought that in order to have a irreversibility theorem, we have to have some inequality that saturates for a conformal field theory. So we were wondering if for a conformal field theory we have a situation where in vacuum you have a saturation of strong subadditivity. And we proved that this was the case for regions like these ones with boundary in a null cone. So we have saturation of strong subadditivity. And here what happens is something, for example, this relation of correlations here is, suppose you have this part, this is like region 1, and this is like region 3. So this is correlated to the other part of the null ray here, and this is correlated with this other part. Both of these are region 2, but they are uncorrelated to each other. So this is how the strong subadditivity saturates in this case. So the idea was then to have a strong subadditivity saturated for a conformal field theory, and then we have to apply strong subadditivity for a theory that is not conformal, non-conformal field theory, so a quantum field theory, arbitrary quantum field theory, which have scales, mass scales. So we are doing this in the cone. Then we are taking some regions in the cone. Here I've drawn many regions. The idea is that you have to use strong subadditivity many times in order to have a relation for the entropies of spheres. So applying strong subadditivity many times, for regions AI, you get this inequality that the sum of the entropies or the variation entropies is greater than the entropy of the union plus the entropy of the union for all pairs of intersections, plus, etc., plus the entropy of the intersection of all regions. And here I'm taking the different regions AI as these regions here. which are just boosted spheres, or one can think that intersections of a plane with a null cone. In Minkowski geometry, the intersection of a plane with a null cone is a sphere. It's not an ellipse or something like that. It's a sphere. And then we are taking as our AIs here all these rotated, boosted spheres. And the regions in the right-hand side of the inequality, these ones, look like this one that is drawn in black here, that I will call them wiggly spheres. In fact, if I take many rotated spheres, I will get regions that approach some kind of a sphere here. But of course, they always have some little wiggles. When I put more and more regions, I will have little wiggles. And I will take the limit. Let us call the radius of the smallest wiggly sphere R, and the largest wiggly sphere will be something like this. I put it capital R. Then it's pure geometry, pure Minkowski geometry, to show that this inequality here, in the limit of large number of rotated spheres, tends to the following. This is the size of the boosted spheres, the original boosted sphere which I rotate, and this is greater or equal than some integral, let me call here. So this L here is just the size of the different wiggly spheres that appear, and this represents the fraction of the wiggly spheres that have this radius L, and you have to sum over all the radius between the smallest one to the largest one. Here. So this can be computed just geometrically. And then if this is like a integral inequality with an integral, but you can take the limit R going to R, to capital R going to R, expand this inequality, and then you get something that, if supposing that we can replace wiggly spheres by spheres, supposing that we can replace wiggly spheres by spheres, then it's an inequality that only involves spheres. If I take this limit, what I get is a differential inequality that looks like the following. Second derivative minus d minus t less than 0. So this is an inequality for the entropies of spheres. So let us check if this inequality holds for the different dimensions in the case where you have a conformal field theory. For a conformal field theory, we expect that this is equal to 0 for a conformal field theory, because we only use Strong's additivity to derive this in the null cone. So it should be always 0. So let us check it. For example, if we have dimension 2, our entropy for spheres, in this case are intervals, is C over 3 log R over epsilon. And the inequality, in this case, reads a second R plus S prime, and this is in fact equal to 0. Okay, so it holds here, no problem. In D equal to 3, we have our entropies are, we have an area term minus the constant F, and the inequality is just second derivative negative. So in this case, we expect equal to 0. And in fact, it's a linear function, so it's okay again. And for d equal to 4, the entropy has, again, an area term and a logarithmic term. And while the inequality reads, in this case, this thing, if this will be 0 if Markovian property hold, but here, if you compute here, this quantity, it gives you h a over r, that not only is different from 0, but is also greater than 0. The anomaly in general is positive. So it doesn't hold. It doesn't hold. So something is wrong. Something is wrong. We have made a mistake in the middle. And the reason is that we cannot replace, in this case, these wiggly spheres by spheres. In d equal to 4, this is different from SL. Even in the limit where the wiggles are arbitrarily small. And we can understand exactly what is the difference, and then we can correct this difference. But another way to do that is to think that we have the Markov property for these wiggling spheres. So we can just do the following. We can, instead of applying the inequality to the entropies, we apply the inequalities to the following quantity, that is the variation of the entropy between the theory with the scales. So this is a quantum field theory. And here I'm subtracting the entropy of the QFT at the ultraviolet. And now I apply strong subadditivity to this. And as this is satisfies strong subadditivity equal to 0, it will not cause any problem. The inequality will be of a strong subadditivity will be obeyed. But now these two quantities have the same structure for. So if I take a wiggly sphere, let's say a wiggly sphere that has some problem here, some term here. These terms are ultraviolet origin, and they get cancelled here. So they can in the delta S, I can replace this by a sphere that is smooth in the limit, and now I get the inequality that I have above, but for delta S. I can also write this inequality. This is in terms of R, like functions of the radius. I can write this as delta S of the area, second derivative, just replacing area equal to R to the power d minus 2. And the inequality takes this form that is nicely independent of the dimension if I write the entropy in terms of the area. So in any dimension is the same. So now we have to understand what this tells us about the terms in the entropy of spheres. As we are subtracting the ultraviolet conformal field theory entropy here. So we have the delta S UV goes to 0, and the infrared delta S, that is for very large spheres, it goes like the difference in the area terms plus the difference in the subleading part, d minus 4 here, plus, etc. And the last terms are different for even and odd dimensions. So this is, sorry. This is delta A. The odd. Now we can apply this inequality here to these expressions. And this inequality tells you that the entropy delta S as a function of area is a concave function. So it's a concave function. Doesn't have a linear term for area going to 0, so it has to be something like this. Asymptotically, it will approach some line here. So from the expression in the asymptotic region for large R, this one, we have two different things. The first one is that the slope for radius going to infinity has to be negative. This means that this quantity is negative. So delta mu d minus 2 is negative. So this can be called some area theorem. In particular, for d equal to 2, I call it area equal to r to the d minus 2, which in this case is log of r. So as the entropy is equal to C over 3 log r, so the logarithmic term is just the area term in d equal to 2. So this inequality tells you that the C ultraviolet minus C infrared is greater than 0. So, and this is the C theorem. For higher dimensions, this tells you something with which is dimensionful. So it's just that the area term renormalizes negatively. In fact, using something that I will not be able to talk about, but there is the derivation is in my notes. This delta mu d minus 2 can be, there is a sum rule for this quantity that can be computed in terms of correlator of the stress tensor traces. And the derivation uses the first law of entanglement. And this quantity turns out to be minus pi over d minus 1, d minus 2, the integral over all Euclidean space so this is a sum rule. As you see, this quantity is 0 for a conformal field theory because it's stress tensor traces, but once you have scales, this is different from 0, and this gives you a number. For some particular theories, this can be even divergent, but there is a negative number. It's a negative number always. interestingly, this same quantity is the Adler-C formula for renormalization of Newton constant. So this delta mu d minus 2 is in fact equal to delta 1 over 4c, where you change the Newton constant between the infrared and ultraviolet because simply you are integrating out the fields, and then this changes the gravity Lagrangian, right? You can do this calculation in two different ways, one in terms of the entropies and one in terms of effective action for the gravity Lagrangian, and they coincide and give you this formula here. And it's natural because you can think this has to be the case because when you integrate out some fields, it will change the thing, and it will also change the as you go, for example, for black holes that are small to black holes that are big, there is a different contribution from the quantum fields around the horizon that adds to the area term. And this ensures that the Beckett-Hawking formula continue to be valid once you integrate out the fields. Well, this was about the area term. So this we said that the slope has to be negative here, but also you have to have the height at the origin of the tangent curve has to be positive here. And you can compute this height at origin just looking at the subleading piece. So the second consequence is that delta mu d minus 4 has to be positive. And this implies that for d equal to 3, implies that delta f is less than 0. This is the F theorem. And for d equal to 4, implies that delta A is less or equal to 0, and this is the A theorem. So then the Strong's relativity inequality has the power to show us all the irreversibility theorems in dimension 2, 3, and 4 by the same calculation. So let me say a few things about this. So the theorem says the same thing for all dimensions. That is this delta S but only reaches the universal parts of the, sorry, instead, yeah, only reaches of let me say better, the universal coefficient, the dimensionless coefficient for d equal to 3 and 4. For higher dimensions, it tells something about the normalization of dimensionful quantities in the entropy of spheres. The second commentary is that unifies all irreversibility theorems. And another commentary is that the only proof for d equal to 3 is entropic. So as we mentioned yesterday, for d equal to 3, the F number is quite non-local. It cannot be related easily to any specific correlator. So this is why the more traditional forms of dealing with this theorem for 3 dimensions didn't give any result yet, let's say. So somehow one could say that it's necessary to have some kind of entropic proof in this case.
Can I ask a question?
Yeah.
You have these less than equal to's in all these formulas. When is it saturated? Are you deforming by an exactly marginal operator?
No, these formulas are saturated for conformal field theories, right?
Right. So you're deforming a CFT by some kind of exactly marginal operator in that case.
No, it will hold also for okay, exactly marginal. Okay, there is something that can be said. So you are asking whether one can say something more in the case that you have a conformal field theory, say a continuous line of conformal field theories, right?
Yes, yes, like K3 or Noreen CFTs.
Yeah, in homological proof of the C theorem in 2 dimensions, it was automatically clear that you cannot have a romanization group running where the endpoints. So let me say like this. So this is not greater or equal to 0, is greater than 0. It cannot be 0 because exactly because of this type of of some rule that doesn't allow you to have a non-zero, a zero change, because otherwise T mu nu will be 0 as an operator. And here we can say the same, of course, for the 2-dimensional case. For the 3-dimensional case, there is something similar can be said, because there is a running of the area term. There is a running of the area term, which also is given by this formula. And you can relate the running of the area term with the running of the F term. Not exactly, but you can prove that the running of the area term implies that there is a running of the non-zero running of the F term. So you can say the same here. This is not less or equal, it's just less than 0. So it may be possible to have theories, different conformal field theories with the same F, but they are not connected by the romanization group flow. For 4 dimensions, we do not know how to say the same thing. It's not clear, yeah.
Right, so if it's not clear, then you don't have a statement about the irreversibility of RG flow, right?
Why?
Because if you can have del A equals 0, then you can reverse RG flows.
Oh, okay, but only for A's. Yeah, okay. Only for the same A's, let's say.
Yes.
Something like that. Okay. Yeah, probably. I don't know. For the same A's, yeah. No, I don't know. I don't know that. But if A changes, it cannot be reversed, right?
Yeah.
Could I also ask a question?
Yeah.
So is this, or how is this related to Kolmogorski's proof of the A theorem? Is this a separate channel? Like you've proven it now also with these entropic functions? Or
Well,
how is it related?
I don't think there is an at least known relation. Is quite different approach. There is something really peculiar that looks like a relation that is interesting, that if you have a, so let me, so you can ask, how are these entropies of region on the null cone for a CFT? And it turns out that these entropies are somehow, so you can actually, for a CFT, you can actually compute exactly the entropy of this region gamma in terms of, is an area term plus some term that depends on A, that is like a Wessumino action. So this is in fact, this entropy of gamma is an action, is a local thing, it's an action for a dilaton on the unit sphere. You can prove that because of Markovianity, that it has to be local. The entropy function has to be local, and also because of Lorentz invariance, it has to be local and conformal invariant, and then there is a classification of the type of action, and you get something. So the problem of understanding how the entropies for a conformal field theory on the null cone is the same problem as understanding actions for the dilaton, conformal invariant actions for dilatons.
Okay.
And that is also the same kind of things that it is in the Komarkovsky-Schwimmer proof, but here is in 2-dimension less. It's an action that depends on a variable on the direction. So it's an action. So the entropy of gamma will be some integral over the angular variables of some Lagrangian, let's say, right, of gamma of omega. But in Komarkovsky-Schwimmer approach, they do it in d dimensions, right? It's just they couple the theory with a dilaton, and then integrate the theory out, and then classify the terms that you get in the Lagrangian for the dilaton. So there is kind of something peculiarly similar, but I don't I don't know how to.
Okay.
Yeah.
Thank you.
Well, let me talk about some few things that are connected to this. The first one is that the Markov property implies the same relation for modular Hamiltonians. So we have, suppose we have this, sorry. Oh, sorry. Then this is exactly the same as saying that the modular. So this is strong enough. It's just a numerical equation. It's strong enough to imply an operator equation. So, and this can be said again, as in the case of the entropy, that this implies some locality for the entropy. This implies then some locality for the modular Hamiltonians. So in such a way that one can say that the modular Hamiltonians is local null line by null line. what does it mean? It means that, for example, in the case of a quantum field theory, if we have the null plane, and one of our regions with some gamma, it means that the model Hamiltonian will be given by an expression that is written in this line independently, is sum over this line, etc. So it's an integral over transversal direction of some operators of the lines, of the null lines. And then it's easy to compute exactly what is the modular Hamiltonian of gamma, which is K of gamma, because we can calibrate what is the operator for this line just using the Rindler case that we know. So it results that K gamma is equal to 2 pi in transversal directions. So it's just this, what I written here is just the Rindler case, but displaced by this quantity in such a way that the coefficient here vanishes exactly at the point of the curve for a given line. So this is interesting because this again is a modular Hamiltonian that is local and is expressed in terms of the stress tensor for all gammas, but it's not as a difference with the case of the Rindler case. In the Rindler case, this modular Hamiltonian is the flux of another current, is a conserved object, so you can write it in any Cauchy surface. Here, this is not in general, this is not a conserved current, so if you write it outside the null plane, it will have an expression, but it will be completely non-local, in general difficult to compute, because you have to evolve the stress tensor from the null surface to another Cauchy surface. So in general, it's non-local outside the null surface. And also the modular flow will be local and look like the Rindler dilatations along the null rays for the case if you live in the null plane, but outside the null plane will be non-local. And the second thing that I wanted to discuss as a consequence of the Markov property is that some unitarity bounds follow from strong subadditivity. So the idea here is that you have like two spheres now, and we take it very separated with a distance L. So this is a sphere of radius B, radius A, let's call it A and B. Very large separation. Well, there is something that I haven't talked about, but when you have this situation, the mutual information can be expanded because you can study first the range entropies, and then you have the twist operators here and here. And as they are very far away, you can use an operator product expansion to expand the twist operators in terms of field operators and to compute these things. And it turns out that in the long distance limit, the mutual information, also the range entropies, are dominated by the lowest dimensional operator of the theory, because it's the one whose correlator is going down slower. And And it turns out that the mutual information in this case is some coefficient times radius of A, radius of B, so over L squared, to the power of twice the dimension of the minimal of the operator with minimal dimension of the theory. So you see here that there is a lot of information, mutual information. In particular, you can extract this, and you can extract many other dimension of the theory, doing an expansion in the large distance limit. And now we will think we have a null cone here, and we have a particular sphere, and I take another one in the same null cone. So this will be A1 and the other one be A2. And here I take very far away some other B. And then I make the strong subadditive inequality, the combination, but for the mutual information. I take EA1B plus EA2B minus EA1 intersection A2B minus A union A2B. And you can see, expanding this in terms of the entropies, that the entropies of A1, A2, A1 intersection, A1 union, because they are living in the same null cone, will cancel because of Markov property. Again, the entropy of B, B, and B will cancel because they are all equal. So at the end, what remains is just the entropies of the unions in the mutual information. So this is equal to minus S A1B minus S A2B plus S A1 intersection A2 union B plus A1 union A2 union B. And now this is a strong subadditive combination, so it has a sign, is negative in this case because it's minus here. So this is less or equal than 0. So we have sign inequality for the mutual information, in this case. And then you can use the game of, again, using a lot of spheres here to produce intersections and union that look like spheres, and use this particular formula for the large distance limit. And what you get is that this implies that delta has to be delta minimum, has to be greater or equal than d minus 2 over 2. So, so this is the unitary bound. In fact, here this expansion is when it's dominated by a scalar field. Otherwise, it has some dependence on the directions of the sphere in space-time. So in this case, you get a unitary bound for scalar fields. And you can also obtain other unitary bounds for different fields, for the fermion field and for other fields, but not all of them, not all of the unitary bounds for all kind of fields, only for fields whose spin structure allows this field for sufficiently low dimension to become free. So it's curious that you have a relation of strong subadditivity with some unitary bounds. So this is usual positivity of Hilbert space. But it's not complete. Somehow the relation is not complete. It's something missing. It's like to obtain all unitary bounds, one would like to have some other kind of inequalities on top of strong subadditivity. And it seems the same is is somehow suggested by the C theory, the irreversibility theorems, because you can obtain from strong subadditivity some inequalities and then prove the irreversibility theorems only for dimension 2, 3, and 4, but you would in principle maybe need more inequalities for proving these irreversibility theorems in higher dimensions. So this is unknown. Okay. So let me see. Okay, well, there's a question about this. I will change subject now. Okay, I will then talk about other kind of applications of thinking in quantum field theory in terms of information theory, things in quantum field theory. And this is about the energy entropy bounds. This subject is quite related to gravity in the limit of G going to 0, so in the semi-classical limit, and it always involves the relative entropy that we have not talked about the relative entropy before, only the mutual information. So let me begin by the Bekenstein bound. It was proposed by Bekenstein as a thought experiment. You have a black hole that is supposed to be very large, and you have a small piece of some matter that is held fixed at infinity by some rope, let's say, and then you release the thing. So at the end, the black hole go to black hole prime, let's say bigger one has swallowed the thing, and here there is nothing. Nothing. So you expect that this quantity, that the change of the entropy of black hole, which is equal to the change of the area over 4c, has to be greater or equal than the change of the entropy outside, because of the generalized second law. So, and then this quantity, the change of the area for a very small perturbation like this, can be computed through the first law of black holes. So Einstein equations, the change of the area is related to energy, and it turns out that this is what you expect thermodynamically is equal to the change of energy over temperature. So we have the black hole space-time here. The energy is the conjugate variable of time, and this is a symmetry that here, very near the horizon, goes like the modular flow, so the boost operator there. So here is proportional to Hamiltonian, and here is proportional to the boost operator. So we can, as our object here was very near to the horizon, we can compute this by computing delta K. So the inequality turns out to be delta K equal greater or equal than delta S. So, and then, well, when Bekenstein did this computation, he said, well, okay, this is the delta S is the entropy of the object that was outside, minus after the object was swallowed, there is nothing outside, so it's zero. So he got an inequality that is the entropy is less or equal, and he thought this term as something like the energy times distance to the boundary, right? It's like the energy of the object, some entropy, and then you have some radius that is bigger than the radius of the object. So you can put here 2 pi radius energy. So, and this is the form that people knows the Bekenstein bound. But okay, but then this inequality seems to suggest that there is a universal bound on entropy given by radius and energy, and immediately you can see that there are some problems with this inequality. So the energy can be negative. The energy for things that are localized in some region of the space in a quantum field theory can be negative, even if the global energy is positive. So this, but of course, but S is positive. And also S is infinity, because it's the entropy of something that is localized. If you have entanglement entropy, if you have a sharp localization, the entropy will be infinity. So these are problems in the precise interpretation of the formula. And also you have this species problem that you can increase the entropy, keeping the energy constant by increasing the number of species, independent species of fields, for example. So these were problems that, but then all of them are solved by thinking modifying this inequality, taking into account the entanglement of the fields. So why is that? Because we have to return to this expression here. And well, the R times E is replaced by something that is more clear now. It's an integral of the stress tensor outside. And this delta S, even if the object was swallowed by the black hole, it leaves the vacuum outside. So this delta S is the entanglement entropy initial minus the entanglement entropy final. So, which is equal to the difference, so is the entanglement entropy of the state minus the entanglement entropy of the vacuum. And this does not have divergences now. So then we have to prove this inequality. We have to prove this inequality, and it turns out that it's simply positivity of relative entropy. To see that, we compute the relative entropy of a state. Global state. Reduce. Yes, reduce. And this is just the trace of rho log rho minus rho log rho 0 that you can write as the trace plus So I'm putting the same thing with different signs here. So the first term is the difference of entropies. So this is minus the difference of entropies between the states, and the second term is this is a log. This is minus the modulo Hamiltonian, and this is just expectation values in different states. So this is delta, the modulo Hamiltonian expectation values between the two states. And this is exactly what we have here. We have the expectation, the difference of expectation values of the modulo Hamiltonians. On the other side, we have differences of entanglement entropy. So this is always positive because this is a relative entropy and it's a positive quantity. So in this formulation, taking into account entanglement of vacuum, we don't have any of the problems. So you can say, well, what happens with the positivity, with the negativity of the energy? Well, there is no problem that this term can be negative, but delta S can also be negative. Entropy is infinity, no, not anymore, because it's a difference of entropies now. And the species problem, it turns out that if you put more and more species, what you get is that these two terms approach to each other, but never violate the inequality. So the quantum Beckett bound holds, but it is not about a limit of number of degrees of freedom. So because of the relative entropy measures distinguishability between states, what the bound really say is that in order, so is delta K equal delta S, in order that you can distinguish a state of the object, for example, from the vacuum fluctuations in a region that is finite, you need enough energy. As much energy you have, better to distinguish the two states, because in that case, the relative entropy, that is the difference between these two terms, will be greater, and then distinguishability is greater, but it's always greater or equal than 0. So there is no bound on the number of degrees of freedom, and also there is no new physics that comes from black hole theory, black holes, to the usual Minkowski quantum field theory. There's no new insight there. So, but it's interesting that the thing of the black hole came to something that was pre-established. Is a pre-established relation between energy and entropy in Minkowski in vacuum and in the Rindel wedge. The expression of the modular Hamiltonian. So this is the first thing I wanted to talk about, and the second one is monotonicity of modular Hamiltonians. Suppose now we have two regions. Let me call this the smaller one A and the bigger one B. And I will call A prime to the complement of A and B prime to the complement of B. So A is included in B and B prime is included in A prime. And then I will compute the relative entropy in the region A between two states, arbitrary states. Yeah, sorry. And this is less or equal than the relative entropy in the region B because of monotonicity of mutual information. And we can do the same. You can do, this is because of this relation, we have monotonicity of mutual information. We can do the same in the complementary region. This is less or equal. And now I am subtracting these two inequalities, in the right way in order to get again an inequality. But first, let me take the second state, rho zero. It's a pure state. Let me take as a pure state. And for a pure state, I can compute the modular Hamiltonian. Let me call them a combination of modular Hamiltonians for a region X minus the modular Hamiltonian of region X prime. Let me call it with this symbol. Let me call it here a full modular Hamiltonian. In fact, people in mathematical community, when they call modular Hamiltonian, they always talk about this quantity because it's well defined as an operator, while this one, as you cut the modular Hamiltonian in the boundary, is not really an operator, but it's a bilinear form. You can compute expectation values, but it's not operator. So, and for a pure state, you can compute this. You can show that this modular Hamiltonian for any region acting on the state phi is equal to 0. You can try to prove it. It's not difficult. For example, use the Schmidt decomposition. So, so why is this interesting? Because now when I subtract these two inequalities, I will have the modular Hamiltonian in A, the modular Hamiltonian in A prime, and when I evaluate it in the state rho 0, they will, because of this relation, will disappear. And also I will have entropies in A and entropies in A prime, and when I subtract them because of the entropy of the state rho 0, let's say, in A is equal to the entropy of rho 0 in A prime, because of the purity of the state rho zero, they also disappear. So at the end, when I subtract these two inequalities under this condition, we get something that seems to depend only on the state rho one. So it seems this expectation value in state rho one, these are entropies for the state rho one that is arbitrary. But here, of course, these modular operators are the logarithms. So they are the full modular operators corresponding to rho zero. But again, this is a pure state that is arbitrary. So one thing is that this quantity, if you choose another Hilbert space, that purifies rho one, you can show that this quantity here is the mutual information between B and Z minus the mutual information between A and Z. So it is a quantity that is always positive. So it turns out that this quantity is always positive for any state rho one. It implies that KB minus KA is a positive definite operator. For any pure state and any regions such that B is greater than A. So, and this has some applications. For example, in the case of, in general, the problem is it would have many applications, but we know very few modular Hamiltonians, right? Exactly understand the structure of the modular Hamiltonian. So let us apply it where we know the structure. That is the case of the null plane again. We have a gamma here. So the K gamma is 2 pi the transversal directions. Right? And then we do just a movement here, very little, in some specific line, some specific point in the transversal direction. We move it inwards in such a way that the new region is smaller, and we use this inequality for the modular Hamiltonians. And it turns out that if you move the gamma, the only thing that changes is this, that is proportional to the integral of t plus plus. It turns out that with that you can prove the expectation value where E is arbitrary, Y is arbitrary, is greater or equal than 0. So the integral along the null line of the stress tensor is always positive. And this is known as the Einek average null energy condition. That it was suspected to be true many years before it was proved. And it is used in several gravity theorems. For example, boundary causality in ADS, non-traversability of black holes. And it is also used in pure quantum field theory. For example, one consequence of this is the Hoffman-Maldacena inequalities between central charges for a safety.
Horacio, you have 5 minutes.
Exactly.
Yes.
Perfect. Perfect timing. Okay. I have 3 minutes. Okay, but I have finished. If people want to ask questions.
That's fine also. Yeah.
Okay.
You're done? Okay. Thank you. Are there any quick questions?
Can I ask a question? So it may be a silly question, but I've always wondered this. So when you do these irreversibility theorems for the normalization group flow, it seems like it's always done in a vacuum state. And I don't really understand why that's always the choice that's made, and perhaps like what would it mean to try to compute, say, this in a thermal state?
Well, the vacuum is because the vacuum is a particular state that is fixed by the theory. So somehow, like if you want to, you don't want to talk about, you want to talk about the theories, right? So if you talk about the vacuum, you are talking about one object that is pointed out by the theory itself, and there is no much details in that. If you take another state, of course, all that I have shown you cannot prove because you need Lorentz invariance. But what you may be asking is, for example, to deform these theorems to theorems on condensed matter, just putting, for example, chemical potentials and temperature.
Right,
like
right.
that.
Yeah, something like that.
Breaking Lorentz invariance with a state. The problem there is, well, we don't have anymore the Lorentz invariance. We don't have understanding of how the modular Hamiltonians behave. I don't know, and also from my point of view, I don't. Maybe people in condensed matter can understand it better, but I don't understand what people would take as good renormalization group flow there, because there are. It's like there are different choices on how you enlarge your region from going to the violet to the infrared, depending on how you move your coordinates, time and spatial coordinates. It doesn't look like there is like unique choice of direction of the flow in this geometrical form of thinking.
So I guess I'm also kind of motivated by seeing like some papers where they apply some of this in holography, and one in which where they compute some C function. In a, say, a Schwarzschild black space-time, and find something that kind of flows upwards instead. So it doesn't, it's not monotonically decreasing, but it's monotonically increasing.
Yeah, well, as I said, it would be very natural and interesting to understand irreversibility theorems in condensed matter. But I think one of the first things one has to discover is what is the thing that really you want to prove, because for me, the renormalization group flow is not clearly defined. Somehow you have to understand what is the formation of space and time, or energy and momentum. Coarse grain momentum and energy maybe in different ways. I don't know.
Okay.
So it's quite open that.
Sure. Well, thank you.
More questions?
I guess related to that previous question, so in a condensed matter system, maybe there isn't such a clear notion of coarse graining, but it seems like there should be some natural way of increasing the size of a system. Like if you have a lattice, and you could just look at a larger region on a lattice, or a larger interval in 1+1 dimensions, or something like that. I was just wondering why this doesn't seem well defined.
Yeah, maybe. But when you do that, in relativity, when you do that, you scale the space and you scale the time at the same time. You have the causal region, and the causal region automatically will scale the same way time and space. But I don't know if you can do something like scaling space, but at the same time changing something like the parameters of the theory such a way that is different, the changing in the time-like coordinates or something like that. Because you don't have this causal structure anymore, right? So or say it in a different way, if you want to change the coupling constant of the theory, but how are you changing the temperature or the chemical potential at the same time with these things? You are changing the spatial scale of your correlators, but you have the freedom to change also the temperature and the chemical potential at the same time.
I see.
I have a question. So the Bekenstein bound was in terms of areas in a bulk region. The relative entropy bound, does that say something geometrical about areas, or is it just about something on the Hilbert space?
The Bekenstein bound, yes, you start with thinking about black holes and areas, but you go to a special limit where the variation of the area can be computed from the stress tensor of the quantum field theory. So it's a limit of small perturbations of the geometry, right? In that limit, it maps to an inequality that you can compute only in the quantum field theory without thinking in a curved space. It's a limit of flat space. And in that particular limit, it is mapped to relative entropy inequality. What happens for non-perturbative variations is not clear for me.
So is this a different bound than, let's say, the Busso bound, or does this contain the same information?
No, I think it's different. It's maybe Busso bound in some limit gives the Bekenstein bound, I think.
Yeah, thank you.
More questions?
Yeah, I have a question. So this average null energy condition, which you said is used in all these theorems in gravity from what I understand, the proof is only really for flat space. And
yes.
So
Yeah,
what are the
the proof
prospects
is-
for you? What are the prospects for using this modular Hamiltonian technology in general curve spacetimes to prove some sort of ANEC or achronal ANEC or something like that?
Well, if you have, I think if you have the case of a space-time where you have a Killing horizon, then all what I said about the Markov property of the entropies of regions with boundary in the Killing horizon will hold. So you have still the Markov property for regions with boundary in the Killing horizon. Of course, this holds only for the state that is invariant in the Killing horizon. Let's say, for example, a thermal state with appropriate temperature for the black hole, the Bekesin, the Hartree-Hawking state for the black hole, or some cosmological state for the sitter or something like that. Then, for that state, you have also the Markov property, and I think you have also then you have also the Markov property for the modular Hamiltonians. So the modular Hamiltonians can be written as an integral of modular Hamiltonians of null lines. And then you have to use this monotonicity for once you have this expression. And I think you get, I haven't seen this, but I think you would get the energy condition if you have a Killing horizon.
More questions? Okay, let's finish there, and thanks, Horacio, again.
Okay, thank you.
And if I don't know, Horacio, can you hang around a little bit? I don't know whether there'll be more questions, but maybe
Let me take out
some
this.
offline questions.